All right, welcome everyone to another deep dive. Today we're going to be tackling Einstein's field equations.
Ooh, exciting.
Yeah, these are pretty intense. But if you've ever kind of like wondered about, what is gravity really? How does it work? Or like how is space and time connected? What is space time? We're going to be talking about all of that today.
Yeah, I think I can help with some of that.
Okay, perfect. So yeah, our goal today is to give you a kind of like a clear introduction, I guess, to these equations. I mean, they are pretty complex.
Yeah.
But I think we can get the core ideas across. And what's really interesting is that, like, a lot of times people think of like, oh, the Einstein field equation, like it's one equation.
Right.
But it's actually a set of 10.
You have 10 independent equations.
Yeah. So it's a lot more complicated than it looks at first glance. So to kick things off, I think we should start with like the difference between Einstein's view of gravity and the classical view, like the Newtonian view.
Okay, yeah. So, I mean, starting with Newton, right?
Yeah.
So Newton had this idea that, any two objects with mass are attracted to each other. And that force of attraction is basically what gravity is, right? And so it's, if you've got two really massive objects, they're going to have a strong force of attraction. And as you move them farther and farther apart, that force of attraction gets weaker and weaker.
Okay.
And that was his law of gravitation. And it worked really well for centuries, right? It explained the motion of the planets. It explained why things fall to the earth. It explained, all sorts of things. But, as with many things in physics, once you start looking at things at a deeper level, and once you start to have, more precise measurements, you start to find cracks in the theory.
Right.
And, one of the biggest cracks in Newton's theory of gravity was that it assumed that this force of attraction acted instantaneously.
Oh, interesting.
So if you were to, suddenly move the sun, the Earth would feel the effects of that immediately.
Oh.
But Einstein comes along and says, well, nothing can travel faster than the speed of light.
Right.
And so how is it possible for this force of gravity to act instantaneously? There has to be some sort of delay, right?
Yeah, that makes sense. Yeah.
It can't just be instantaneous.
Yeah.
And so, this was one of the big puzzles that Einstein was trying to solve.
So how did he kind of reconcile those two things? How did he bridge that gap?
Well, the key insight, one of the key insights was this thing called the equivalence principle.
Okay.
And the equivalence principle basically says that you can't tell the difference between being in a gravitational field and being in an accelerated frame of reference.
Okay.
So, the classic example is, imagine you're in an elevator and the elevator is accelerating upwards.
Right.
You're going to feel, heavier. You're going to feel like there's a force pushing you down. But, there's no way for you to tell whether that's because you're in a gravitational field or whether it's because the elevator is actually accelerating.
Oh, okay. Interesting.
And so Einstein took this idea and he ran with it. And he said, well, if you can't tell the difference, then maybe they're actually the same thing.
Wow.
Maybe gravity is just a consequence of being in an accelerated frame of reference. And so that was a big part of the insight.
Okay. And so then how does that relate to light?
So, again, with the elevator example, right?
Yeah.
If you're in this accelerating elevator and you shine a beam of light across the elevator, well, by the time the light reaches the other side of the elevator has moved upwards.
Right.
And so to an observer inside the elevator, the path of the light is going to look like it's curved.
Okay.
It's going to look like it's bent downwards. And so Einstein said, well, if gravity is just an accelerated frame of reference, then gravity must also bend light.
Right. Okay. Yeah, because if you can't tell the difference between being in a gravitational field or accelerating,
Exactly.
then light must bend in both situations.
Exactly. And, this was a pretty radical idea at the time because, Newton's theory of gravity said that light shouldn't be affected by gravity at all because light doesn't have any mass.
Right. Yeah.
And so, but Einstein was saying, well, no, actually, light is affected by gravity because gravity is not a force. It's a curvature of space-time.
Right. Okay.
And so this was a huge, huge shift in our understanding of gravity.
And this was something that was actually experimentally verified.
Right. Yeah. So in 1919, there was this famous solar eclipse expedition. And astronomers went out and they measured the position of stars that were very close to the sun during the eclipse. And what they found was that the position of those stars was slightly shifted from where it should have been.
Okay.
Because the light from those stars was being bent by the sun's gravity.
Oh, wow.
And the amount that the light was bent was exactly what Einstein's theory had predicted.
Oh, wow. That's amazing.
And so that was a huge confirmation of Einstein's theory.
Yeah. So if gravity's not this force that's pulling objects together, then what is it in Einstein's view?
So Einstein said that gravity is not a force, it's a curvature of space-time.
Okay.
And so what does that mean? Well, it means that, space and time are not these absolute unchanging things.
Mm-hmm.
They're actually flexible.
Okay.
They'd be warped and curved by the presence of mass and energy.
Right.
And so what we perceive as gravity is actually just objects moving along the straightest paths they can in this curved space-time.
Okay.
So imagine you've got a bowling ball on a rubber sheet,
Right.
right? And the bowling ball is going to create a dip in the rubber sheet.
Right.
And then if you roll a marble across the rubber sheet, the marble's not going to go in a straight line anymore. It's going to curve towards the bowling ball.
Okay, yeah.
And it's not because the bowling ball is pulling on the marble with some mysterious force.
Right.
It's just because the marble is following the curvature of the rubber sheet.
Okay, I see.
And so that's kind of the analogy for what's happening with gravity.
So the bowling ball's like a star or a planet.
Exactly. Yeah. And the marble's like, a planet or comet or something like that.
Okay.
And the rubber sheet is space-time.
Yeah. Okay, so then what is space-time? I mean, you're saying it's like this rubber sheet, but...
Right. So space-time is the combination of space and time.
Okay.
So, we normally think of space as, 3 dimensions.
Yeah.
Up, down, left, right, forwards, backwards.
Mm-hmm.
But Einstein showed that time is actually a 4th dimension.
Okay.
And so, all events in the universe happen in this 4-dimensional space-time.
Right.
And so, when you're moving through space, you're also moving through time.
Okay.
And, the way that you move through space-time is affected by the curvature of space-time.
Oh, right.
Which is affected by the presence of mass and energy.
So it's like, so anything with mass or energy is going to warp space-time?
Exactly.
Okay.
Yeah.
And then that warping is going to affect how other things move through that space, through space-time, I guess.
Exactly. Yeah.
Okay, wow. That's pretty mind-blowing.
Yeah.
So let's get into the actual equations now, like the Einstein field equations. What do they tell us? Like, what are they?
Okay, so the Einstein field equations are basically the mathematical equations that describe how mass and energy curve space-time.
Okay.
And they're pretty complicated, but I think we can kind of break them down into 2 main parts.
Okay.
So on one side of the equation, you've got the curvature of space-time.
Okay.
And on the other side of the equation, you've got the distribution of mass and energy.
Right.
And so basically the equations are saying that these two things are proportional to each other.
Okay.
So, the more mass and energy you have in a particular region of space, the more curved space-time is going to be in that region.
Okay, yeah.
And vice versa.
Okay.
So, if you've got a really massive object like a star, it's going to create a big curvature in space-time.
Right.
And that's why, planets orbit stars.
Yeah.
Because they're following the curvature of space-time that's created by the star.
Okay, so can we break down those sides of the equations a little bit more? Like you said, on one side, there's the curvature of space-time. What exactly is going on that side of the equation?
Right, so the curvature of space-time is described by something called the Einstein tensor.
Okay.
And I know that sounds really scary and technical.
Yeah.
But basically just think of it as like a mathematical object that describes how curved space-time is.
Okay.
Like at any given point in space-time, you can calculate the Einstein tensor, and they'll tell you, how curved space-time is at that point.
Okay. Interesting.
And the Einstein tensor is actually derived from a couple of other mathematical objects. One of them is called the Ricci tensor.
Okay.
And the other one's called the Ricci scalar.
Oh, okay. Yeah.
And they're all just different ways of measuring the curvature of space-time. Okay.
And importantly, this side of the equation also involves the metric tensor.
Right, the metric tensor. So that's kind of like the ruler of the universe, right?
Exactly, yeah. So the metric tensor is what tells you how to measure distances in space-time. So, like if you've got 2 points in space, the metric tensor will tell you how far apart those 2 points are.
Okay.
And it also tells you how to measure angles.
Okay.
And, all sorts of other geometric things.
Right.
And so the metric tensor is really important because it's what determines the geometry of space-time.
Okay.
And the curvature of space-time is basically just a way of saying that the metric tensor is changing from place to place.
Okay, okay.
So if the metric tensor is constant
Right.
everywhere, then space-time is flat.
Okay.
But if the metric tensor is changing,
Mm-hmm.
then space-time is curved.
Okay. And so mass and energy is what causes the metric tensor to change.
Exactly, yeah. Okay. So then on the other side of the equation, the mass and energy side, what's going on over there?
Right. So on the mass and energy side, we have something called the stress energy tensor.
Okay.
And the stress energy tensor is basically a mathematical object that describes the distribution of mass and energy in space-time.
Okay.
So, it tells you how much mass is at each point in space-time. It tells you how much energy is at each point in space-time.
Okay.
It tells you how fast the mass and energy are moving.
Okay.
It tells you, all sorts of things about the mass and energy.
Right, right. So it's really kind of like a very detailed accounting of all the stuff that's in space-time.
Exactly, yeah.
Okay. So then, like, I remember you mentioned the cosmological constant earlier.
Oh, right.
Where does that fit into all of this?
Right. So the cosmological constant is a term that Einstein added to his equations in 1917.
Mm-hmm.
And at the time, he added it because he thought that the universe was static,
Okay.
that it wasn't expanding or contracting. And so he needed some way to counteract the pull of gravity.
Okay.
Because if gravity is the only force that's at work, then the universe should be collapsing in on itself.
Right. Yeah.
And so he added this cosmological constant as like a repulsive force
Okay.
to kind of balance out the attractive force of gravity.
Okay. So it was kind of like a fudge factor to make the universe.
Yeah, basically.
Fit his model of the universe at the time.
Exactly, yeah. But then, a few years later, astronomers discovered that the universe is actually expanding.
Right.
And so Einstein was like, oh, whoops, I don't need that cosmological constant after all.
Right, yeah.
And so he famously called it his biggest blunder.
Right, right.
But then, fast forward to the late 1990s,
Mm-hmm.
and astronomers discovered that the expansion of the universe is actually accelerating.
Okay.
And so now physicists are like, wait a minute.
Maybe we do need that cosmological constant after all.
Maybe we do need that cosmological
It's not
constant
true.
after all.
Yeah. Yeah. Wow. So now it's kind of like back in vogue again.
Exactly, yeah.
Okay, interesting. So these Einstein field equations, you mentioned they're pretty complex. They're nonlinear. They're partial differential equations. What does that mean? Like, why is that important?
Well, it's important because it means that they're really hard to solve.
Okay.
Like a linear equation is an equation where, the variables are all like just raised to the first power.
Okay.
And so it's pretty straightforward to solve a linear equation.
Okay.
But a nonlinear equation is an equation where, the variables are raised to higher powers or they're multiplied by each other.
Okay.
And so that makes it a lot more complicated to solve.
Right, right.
And then a partial differential equation is an equation that involves, derivatives of multiple variables.
Okay.
And so, again, that makes it more complicated to solve.
Mm.
And so the fact that the Einstein field equations are all of these things, nonlinear and partial differential,
Mm-hmm.
it means that they're really, really hard to solve.
Right. Okay. So how do physicists actually use these equations then if they're so difficult to solve?
Well, a lot of times what they do is they make approximations.
Okay.
So they say, okay, well, we know that the equations are really hard to solve in general,
Mm-hmm.
but let's say that we're only interested in a particular situation.
Okay.
Like, let's say that we're only interested in the gravitational field of the Earth.
Mm-hmm.
Well, in that case, the Earth's gravitational field is relatively weak.
Okay.
And so we can make some approximations to the Einstein field equations.
Okay.
And those approximations will make the equations a lot easier to solve.
Okay.
And so we can get a pretty good solution for the Earth's gravitational field, even though we can't solve the equations exactly.
Okay.
And so that's what physicists do a lot of the time is they make approximations.
They kind of like simplify it down to a manageable level.
Exactly, yeah, yeah. And another thing that they do is they use computer simulations.
Okay.
So, computers are really good at solving equations.
Mm-hmm.
And so you can program a computer to solve the Einstein field equations.
Okay.
And it'll give you, a numerical solution.
Right.
Which is, not an exact solution,
Mm-hmm.
but it's pretty good approximation.
Okay. Okay. So So there are ways to get around the difficulty of solving these equations, but they're still incredibly useful.
Right, exactly.
Okay. So what are some of the the fundamental things these equations that have to be true because of these equations?
That's right. So one of the most important things is that these equations imply that energy and momentum are locally conserved.
Okay.
So what does that mean? It means that if you take any small region of space-time,
Mm-hmm.
the total amount of energy and momentum in that region has to stay the same.
Okay.
It can't be created or destroyed.
Okay.
It can only be moved around.
Yeah.
And so that's a really important principle in physics.
Mm-hmm.
And it's something that's built into the Einstein field equations.
Right. Okay.
So those are really important. And then, another thing that I think is worth mentioning is that the Einstein field equations are actually a classical theory of gravity.
Okay.
So what does that mean? It means that they don't take into account quantum mechanics.
Right. Right.
Which is the theory that describes how things work at the very smallest scales.
Okay. Yeah. So atoms and subatomic particles.
Exactly. Yeah.
Okay.
And so, one of the big challenges in physics today is to try to combine general relativity,
Mm-hmm.
which is the theory that's described by the Einstein field equations,
Right.
with quantum mechanics
Okay.
into a single theory of quantum gravity.
So that we have one theory that can describe everything.
Exactly. Yeah. And so that's a really active area of research right now.
Oh. Right, right. So even though we can't solve these equations exactly, and even though there's still a lot that we don't understand about them,
Mm-hmm.
they've been incredibly successful in explaining, a lot of things about the universe.
Oh, absolutely. Yeah. I mean, they've really revolutionized our understanding of gravity,
Mm-hmm.
and they've led to all sorts of predictions about the universe that have been confirmed by observation.
Right, right.
So, one of the things that the Einstein field equations predict is that light should bend around massive objects.
Right.
And we've already talked about how that was confirmed by the 1919 solar eclipse expedition.
Yeah, yeah.
But, that's just one example.
Okay.
There are many other examples of predictions that have been made by the Einstein field equations that have been confirmed by observations.
Okay, what are some of those? What are some other cool things?
Well, another thing that the Einstein field equations predict is that time should slow down in strong gravitational fields.
Okay, that's weird.
Yeah, so, if you have a clock that's near a massive object like a black hole,
Mm-hmm.
that clock is going to tick slower than a clock that's far away from the black hole.
Oh, wow. Okay.
And this has actually been measured.
Okay.
They've put atomic clocks on satellites,
Mm-hmm.
and they've measured the difference in the ticking rate of the clocks.
Wow.
And it matches exactly what the Einstein field equations predict.
Oh, wow. That's incredible. So it's like literally time is relative.
Yeah, exactly. Time is relative, and it depends on your position in a gravitational field.
Wow.
And the Einstein field equations are what tell us how to calculate that difference in time.
Okay. Okay.
And another thing that they predict is the existence of black holes.
Right.
So black holes are regions of space-time where gravity is so strong that nothing, not even light, can escape. And the existence of black holes was first predicted by solving the Einstein field equations.
Oh, wow.
And it wasn't until many years later that astronomers actually found evidence for black holes.
Mm-hmm.
But the fact that they were able to find evidence for black holes is another huge confirmation of the Einstein field equations.
Right. Right. So these equations are really they're super important for understanding some of the most extreme objects in the universe.
Exactly.
Like black holes.
Yeah.
But they also play a role in cosmology, right?
Oh yeah, absolutely. So cosmology is the study of the universe as a whole.
Okay.
And the Einstein field equations are essential for understanding cosmology.
Okay.
Because they tell us how the universe is evolving over time.
Right.
So, if you take the Einstein field equations and you apply them to the universe as a whole, you can derive the equations that describe the expansion of the universe.
Yeah.
And those are called the Friedmann equations.
It's Friedmann equations, okay.
And the Friedmann equations are really important because they tell us how how the universe has been expanding over time.
Mm-hmm.
And they also allow us to predict how the universe will continue to expand in the future.
Right. Okay.
So the Einstein field equations are really at the heart of our understanding of the universe on the largest scales.
Yeah. Wow. That's incredible. So to kind of like wrap things up here, what would you say is like the most profound takeaway from all of this, from these equations?
Well, I think the most profound takeaway is that gravity is not a force.
Okay.
For centuries, we thought of gravity as this mysterious force
Yeah.
that acted at a distance.
Right.
But Einstein showed us that gravity is actually a curvature of space-time.
Okay.
And that's a really, really profound idea.
Yeah.
Because it means that space and time are not these absolute unchanging things.
Right.
They're actually dynamic.
Yeah.
They're flexible.
Yeah.
They can be warped and curved by the presence of mass and energy.
Right. Right.
And so that really changes our whole picture of the universe.
Yeah. It kind of changes like our fundamental understanding of reality almost.
Yeah, exactly.
Yeah. Yeah. Well, this has been amazing.
Yeah, it's a really fascinating subject.
I have to say, like, I knew these equations were important,
Hmm.
but I didn't realize just how much they affect everything.
Yeah, they're really at the heart of our understanding of the universe.
Yeah. Well, hopefully, this has inspired some of you listening to go out and learn more about this stuff.
Yeah, absolutely. I encourage you to do some more research. There are some really great resources out there.
Yeah. And if you can understand these equations, then you've got a pretty good grasp of modern physics.
You're well on your way. Yeah.
Yeah. So good luck with that, and we'll see you next time for another deep dive.
All right. Sounds good.